Hello my students, your physics teacher Hassan Darwish with you. In this video, I'm going to continue the explanation of chapter 3 about the angular momentum. Remember, in the last 3 videos, I explained objectives 1 and 2. Define angular momentum, state and apply the theorem of angular momentum. Now in this last video, I will explain objectives 3 and 4. Identify the condition of conservation of angular momentum. Apply the law of conservation of angular momentum to solve problems. Okay, let's start. Remember? Now, conservation of angular momentum. It's like the conservation of energy or mechanical energy and conservation of linear momentum. There are conditions, okay? So here, what is the condition to have the angular momentum of a particle or a system of particles conserved? Here, if sum of moment is 0, momentum is 0, because you remember this rule, okay? Remember the theorem of angular momentum. Sum of moment is equal d sigma, okay, over dt. Remember, that's the theorem of angular momentum, or is equal sigma prime, okay? So if sum of moment is 0, then derivative of angular momentum is 0. Then if the derivative is 0, then the quantity is constant, right? Constant means doesn't change with time. So we say it is conserved, as we did with mechanical energy and linear momentum. So we obtained the initial angular momentum is equal to the final angular momentum, or the angular momentum of the system at an instant t1 is equal to the angular momentum of the system at another instant t2. Okay? This is everything about conservation of angular momentum. Let's do an application on this. Okay. Here we have a door of width 1 meter. This is 1 meter. Length 2 meter. Here is the length. 2 meter. Okay? And this off. And here. It is hinged on one side so that it can rotate without the friction about the vertical axis through the hinges. Here are hinges. Clear? And this is the vertical axis. Now we have here a bullet, mass 10 gram, and the speed 400 meter per second in the exact center, okay, of the door. Determine the angular speed of the door just after the bullet embed itself in the door. The bullet is embedded in the door, okay? So here it is logical to think of the conservation of angular momentum. Why? We always, when we have collision and rotation, try to think of the conservation of angular momentum. But first, you have to prove whether the angular momentum conserved or not. Okay, let's check the conservation of angular momentum. Here, our system is the bullet plus the door. Okay, bullet plus door. Now, what are the forces acting on this system? External forces. Okay, let's go back here. Now, external forces are, we have the weight before and after collision. We have the weight of the bullet, mg, which is vertically downward. We have the weight of the door, right? Also vertically downward. And we have the reaction of the hinges, R. Okay? But notice here, the three forces, mg, and R, are vertical forces, means they are parallel to the axis delta. Here is delta. Don't forget. Consequently, the moment of these forces is zero. So sum of moment is zero, means angular momentum is conserved, right? So here, external forces, as we said, mg and R, but sum of moment with respect to delta is equal to the moment of weight of the bullet plus moment of the weight of the door, okay, plus moment of the reaction. But because, and you have to mention this in the exam, is zero, okay, so angular momentum is conserved, isn't it? I mean sigma of the system here, not of one body, is conserved. What does this mean? It means that sigma initial equals sigma final. But what is the initial state here? Before collision, right? So sigma before collision is equal to sigma of the system after collision. Okay? Before collision, you know, our system consists of two objects, right? Here, the bullet and the door. So sigma of the bullet plus sigma of the door is equal to sigma bullet plus door, right? You remember the rule of the angular momentum, whether it is a particle or a rigid body, it means I theta prime. But here don't forget, this is I of the bullet, theta prime of the bullet, and this is I of the door, theta prime of the door equals, now the bullet and the door become or form one rigid body in rotation. So its angular momentum is I of the system, which is I bullet plus I of the door, the prime of the system. Clear? Now let's, for example, here resolve the moment of inertia I for each object. First of all, here we have, this is 0. Why? Because the door is at rest before collision, and consequent angular speed is 0. This is only theta prime. Okay? So what we have here, you know that for a particle, for a particle, I is mr squared. Okay? There's a problem here with active inspire. So r squared, this is the times theta prime for the bullet is equal m r squared, this for the bullet, plus m d squared over 3, this is I for the door, which is given, right? This is given. And this is theta prime. Now what is r? But let me first simplify more the calculation. You know theta prime is v over r. So this is mr squared times v over r for the bullet is equal theta prime. This quantity theta prime. Okay? R with R cancel. But what is R? The value of the radius of the circle. Let me go to the question. Here is the bullet. Clear? The radius is this distance. Put it in blue. Here is R, which is half the width, because here is the axis and here is the particle. So the circular motion of the particle around this axis is this circle. Okay? So R is half D. Half D. So m d over 2 v is equal to m d squared over 4, because radius d over 2, radius squared d squared over 4, plus m d squared over 3, right? Now we have d 1 meter, we have v 400 meter per second, we have m 10 gram, 0.01 kilogram, and this mass is 6 kilogram, and this is theta prime, right? So if you do the calculation, then you get theta prime is equal to 1 radian